aromatic hydrocarbons. These are very stable, and they're based on the benzene ring, and that is C6H6. So each one of these carbons only has one hydrogen coming off of it. So therefore we know it has something like double bonds alternating with single bonds, right? So like I've drawn here, double, single, double, single, double, single. And technically you could draw it with the double bonds in a different place where the single bonds were. Okay, but what we do know is all of these bond lengths are exactly the same. And so we know it's not actually alternating single double bonds. They have different bond lengths, single bonds and double bonds. So these are all the same and they're the same strength. So we know it's not, the best way to draw it isn't like these two, but we've drawn the structure like that for a very long time. But this basically satisfies the bonding that there's only one hydrogen available to bond on each carbon. So the compounds that we've looked at already, alkenes, alkynes, alkanes, are called aliphatic compounds because they are straight chains. And these special kind of hydrocarbons that contain this ring structure of benzene are called aromatics. So basically what happens is, with this cyclic system in benzene, we have delocalized electrons. That means electrons are free to roam across all of the carbons. We cannot pinpoint them down into one single or double bond. And this is because of this terminology called conjugation. And conjugation means double, single, double bond. So they're not available, these electrons are not available to bond in chemical reactions. So this structure is very, very stable. There is a newer, better way to draw benzene, and it's basically a resonance of these two. And we basically put a circle inside, and that represents the electrons moving around in that carbon structure. So this is the best way to draw benzene because it doesn't actually have any single or double bonds like the older two structures show. So benzene is the root of our name, and if this side group contains 6 carbons or lower, then we prioritize them alphabetically. Carbon number 1 goes to the first alphabetical group, and then you number in the direction to make sure you get the lowest possible numbers. So let's look at these two examples. So this first one here on the left. Here's your benzene ring, and there's a methyl group on it. Because there's only one side group, it's understood that that is at carbon number 1. So we do not need a number, just like we didn't with the cyclic hydrocarbons. So this is just methyl benzene. This middle structure here has 2 side groups, so we're going to need numbers to say which carbons they're on. So the root is benzene, and we have 2 side groups, but they only contain 1 carbon. So this is a dimethyl. They're the same side group, so you pick one of them to be carbon number 1 in the benzene ring. So I'm just going to pick the top one to be 1. So if that's 1, then count in the direction that gives you the lowest number. So that would be counterclockwise. So that would be carbon 2, and this would be carbon 3. So this is 1,3 dimethyl benzene. carbon number 1, carbon number 2, carbon number 3. So we've got a methyl group on carbon number 1 and carbon number 3. All right, last example. We have the root benzene again, but this time we have two different side groups. We've got a methyl group and an ethyl group. So E comes in the alphabet before M, so therefore priority number goes to the E, the ethyl. So this would be carbon number 1. And then the methyl is on this carbon right beside it, so that's carbon number 2. So this would be 1 ethyl, 2 methyl, benzene. If benzene then is attached to a carbon chain that contains 7 or more carbons, then it's considered a side group, just like it was for the cyclic hydrocarbons. But this time it's given a name, phenyl. So the same rules apply as they were before. Okay, so here's our benzene group. And the carbon chain is 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 is bigger than 6. So there's no double or triple bonds. So this is nonane. This is the alkane carbon, 9 carbons, so that's nonane. And the side group is on carbon number 3. So this would be 3 phenyl nonane. Now, for benzene, you're going to find that there are common names on the internet if you search up a structure. For instance, methylbenzene is often called toluene, but we name using IUPAC rules. So I'm expecting IUPAC rules, not common names. So when you draw compounds containing benzene, you use the line diagram. It's the best thing to do, with a circle in the middle, and then place side groups on benzene as dictated by the carbon number. For instance, 1,2-dimethylbenzene. So draw your benzene. Carbon number 1, pick a carbon to be carbon number 1. It's always convenient to put it at the top. And the next carbon beside it would be carbon number 2. So there you go, 1,2-dimethylbenzene. Now, if you see a structure and you have to name it, don't forget that you can rotate this molecule. This is the exact same thing. These are not isomers. This is the exact same compound. This is 1, 2, 1, 2 dimethylbenzene. Now, physical properties. Benzene is a rather unusual compound. It's a liquid at room temperature. It's got a very strong odor, and it's non-polar. So it's used very frequently in organic chemistry as a solvent. It has only London dispersion forces as its intermolecular forces. But due to its flat structure, it's a planar molecule. The carbons, the hydrogens are all in the same plane. It's completely two-dimensional. So because it's flat, the molecules can come really close to each other. So those London dispersion forces are felt quite strongly. It's a very unique structure.